Welcome to another video in the series about the tiarmclang compiler. This video explains a feature of the compiler called link time optimization. My name is George Mock and I'm your guide. Throughout this presentation, the acronym LTO stands for link time optimization. That's how I will say it most of the time. LTO is introduced in the compiler version 2.1.0.LTS. This is the compiler and the linker working together to provide an even higher level of optimization. And what does this mean? Well, it means significant reductions in code size and execution time. What's the call to action here? What is it we'd like you to do? Well, we'd like you to always compile with the option -f-LTO to enable link time optimization. This is true especially if you are building a library. Also, always link with the same option, okay? For those of you who use CCS, even though this is a compiler and a linker option, you set -f-LTO only in one place. For those of you who just want to know what am I supposed to do, well, you're done with this video. You can stop watching right now, but I'm pretty sure most of you want to know, well, why would I do it? Well, that's what the rest of this video is about. Before we get into that, I want to show you how to set FLTO in a CCS project. So, right-click on the title of the project, show build settings, and you want to browse to build ARM compiler optimization right there in this collection of compiler options, and this is the one that will be available to you if you are using compiler version 2.1.0.LTS or later. Select link time optimization. You turn that on right there, and that's it. During the next part of the video, I'll talk over parts of the compiler manual, so I want to show you how to get to the manual. Right now we're on the home page for the tiarmclang compiler. It's already on the complicated variant of the URL. That's not what I want you to remember. What I want you to remember is this right here, ti.com/tiarmclang. That's what you enter, and that's automatically redirected to here. Okay. And one of the early things on the page is a link to the compiler manual. Click that. Here we are. This is the compiler manual for online compiler manual for tiarmclang. You know, several elements to it. I'm going to get into the compiler tool users manual, and it's got a chapter just on link time optimization, and here it is. Let's start into the chapter. The first part of it is an example. In the interest of time, I'm going to skip over the example. I want to focus on the code size reduction. So we have some data here summarized in a table. This table right here. Let's walk through this a little bit. The first column is which processor did this collection of applications run on. In this case, the M0 Plus driver libraries, and there are 191 of those. Okay, run on a Cortex M0 Plus processor, and we saw a code size reduction of 23 to 25%, which is a very aggressive number. Where'd this come from? Well, we built these 191 applications first with -OZ, get that baseline number, all right, and then we add -FLTO. So we built the second build with combines both -OZ and -FLTO, and then we look at the code size numbers again, and we this right here is the details on the computation. You know where these numbers come from. They were computed using that little computation right there. we're trying the best we can here to be as transparent as we can, because we realize that, you know, making the claim of this kind of code size reduction is a significant claim, and we're trying to give you confidence that when you try and do this yourself on your build, you're going to see similar results. All right, so let's look at the second row. SDK stands for Software Development Kit examples. There were 362 of those. Targeting a Cortex M4 system, the numbers in that case came to 6 to 11% smaller code size. And then the third column is some Embassy Auto Bench applications. There were 15 of those, targeting a Cortex R5 system, and the numbers were 4 to 8% smaller. So here's an example of a very good reason to turn on -FLTO in your builds. Next, let's look at performance, which is the data in this table here. It's not exactly as the table above. It's put together a bit differently. For all three rows, it's the same collection of applications. So 15 auto bench applications. We built them for, you know, M0 plus, M4, M5. Here's how the speed up factor column is computed. That's right there, and then percentage reduction in cycles. That's right there. You know, just two different ways of expressing the same thing. Just you know, whichever way you prefer to think about it. We show it both ways. Again, these are some aggressive claims. 1.2 fat speed up, just from using -FLTO, and let me flesh that out in a little bit more detail. So we build the application with -03, which is different than -OZ. With -OZ, you're saying I care mostly about code size. With -03, you're saying I care mostly about making it run fast. Okay, so we built with -03, and then we add -FLTO. So the second build uses both 03 and -FLTO, and then we compare those two builds with regard to how quickly do they run, and break those numbers down, you know, two different ways. And that's what you see for Cortex M0 Plus. Speed of 1.20, a reduction in how many cycles is 3.8%. M4 1.12, 4.4%. R5 1.17, speed up factor getting close to 1.2. Reduction in cycles 9.3%. And if you want details about, you know, exactly how the cycles are computed or counted and so on, I mean, all of that is right here. Again, we're trying to be as transparent as we can, because we know these are some really aggressive claims just for a single compiler option. But here it is, folks. This is a great reason to use -FLTO. Let's go to the next page and start talking about the LTO development flow. So this part of the video is for those of you who have some interest in the details of how LTO works under the covers. How is this, you know, really happening? How is the compiler and the linker working together to make this happen? And the way I like to do it is by focusing on this diagram here. It's a pretty busy diagram. There's a lot going on in it, and so I'm going to start with a really simple example, one that's really not realistic, but it's a great place to start understanding how this works under the covers. Let's make the picture bigger. So in this example, presume your program has only a few C files and no libraries. Again, not realistic, but a good place to start. So for this walk through the diagram, we can ignore those three sort of starting points. Just ignore them, pretend they don't exist. We're going to start here. Your entire program is nothing but some C files, and you build all of those C files with -flto. Well, that will cause the compiler to compile each of those files, but in addition, it adds some what we call embedded IR to each object file, where the term IR stands for intermediate representation. So in addition to the ordinary object file, there's extra information in that file that we call embedded IR. Okay, so in this part of the diagram right here, we're talking about you link with -flto. Okay, well, what happens there? Well, the IR is extracted from each of the object files, okay, and then it's all merged together to form this combined intermediate representation, okay, and then the compiler is invoked a second time, okay, except it's working on all of the intermediate code from all of the C files all at the same time. And this opens up opportunities for optimization that you just don't see in ordinary compilation where you're building a single file at a time, okay? That's what we call inter-module optimizations. That ultimately generates an LTO object file, which goes on into the traditional linking process, and then finally an ELF executable that you're used to. So for the simple case of just a small collection of C source files that are built with FLTO, you kind of flow through like this. All right, so not what people really do in real life, but in terms of building up an understanding of how this all works, it's a great place to start. Now let's add in one layer of complication, and that layer of complication is, let's say there's a library of C and C++ source files that are built with FLTO. Okay, so that's going to add in this path into the diagram. So again, in this thought experiment example, I've got a few C files that are built with FLTO, and they're going to come in through this path. And then we're going to have one library, some collection of, say, just C files, also built with FLTO. They're going to go through that path. Okay, so we know what happens here. Let's consider the library case. So, collection of C files, they become a library. You build them with LTO. That's a bunch of object files that have embedded IR in them. tiarmar, that's the archiver, that's the tool you normally use, LTO or not, to create a library. .a is the typical file extension for a library. Sometimes you see .lib or other things, but .a is the typical name. So coming into the link, you have a few object files that were built this way in one library, okay, and coming into the link, that's also occurring with LTO enabled. What happens? Well, the C files, we've already walked through that. It's a really similar story with the members of the library that are used by the program. The object code has the embedded IR in it. That IR is extracted. It's all merged together, and this combined IR in this case comes from these object files and the object files from the library, and then the compiler is invoked a second time, and it's looking at all of this code at once. So the C files from the user code, the C files from the library, they're all being optimized together. Inlining's happening, and other interesting optimizations that just rarely happen outside of doing this sort of thing. Creates an LTO object file, goes into the traditional link, finally producing an ELF executable that you're accustomed to. So the point of this thought experiment is to illustrate why it is, early on in this video I said if you're building a library, always build -FLTO. Always enable LTO when you're building that library. That's so it can participate in the optimization that happens at this phase. Now add in an additional layer of complication, and that layer is represented here. Say you've got some assembly code that obviously cannot be built with LTO enabled. What happens in that case? So again, we've got some C files built with LTO, one library built with LTO, and now additionally some assembly code not built with LTO. What happens in that case? For any of the code built with LTO, and therefore it has embedded IR, it goes through this path. The object files without embedded IR, at link time, they are recognized, here at this level, and they just get forwarded straight on to the traditional link step. And in fact, that happens no matter how some object file manages to get to the link and it doesn't have embedded IR in it. So assembly code is one way that can happen. Assembly code inside a library is another way it can happen. Yet another way it can happen that isn't even represented here. Let's say you have a library that for whatever reason just isn't built with LTO. Its object files are going to show up here with no embedded IR in them, and they'll get forwarded to the traditional link step. So the traditional link step is now dealing with an object file that was, comes from the LTO optimization. Multiple object files that are built the traditional way without LTO, and then they are all linked together into ELF executable that you're used to. This all works just fine in terms of correctness and that sort of thing. With regard to any C code that somehow gets to this point and it doesn't get to participate in this optimization, that's unfortunate, and we're trying to do everything we can to prevent that from happening because of the the optimization that you're leaving behind on the table whenever you do that. Before we close out this video, I want to give you a couple of references. The first one we actually used during the video. This is the homepage for the tiarmclang compiler, ti.com/tiarmclang. As you've seen, you can access the manual. This is also where you can download the compiler and more details like that. The second reference is to e2e.ti.com. This is where you go to ask any question on any TI product, including tiarmclang. If that question happens to be related to the compiler, that question will be answered by me. Thank you for watching this video in the series about the tiarmclang compiler.